Hi everyone, this is lesson 2 of chapter 19 for astrophysics. We're going to be looking at electromagnetic radiation coming from stars. So we're going to look at some key things here, which you will help you understand how scientists know what stars are composed of. You already know something, so we'll be working through the things that we already know and introducing some more new things as well in here. So we're going to be looking at energy levels of electrons, why they have negative values. We'll also look at emission spectra lines from hot gases. We will also use the equations that we have seen before in quantum physics, so the energy of a photon, but in this case we're going to link it to the photons involved in the energy levels. Also that different atoms have different spectra lines, which helps identify elements, which we will talk about. And we will look at the continuous spectrum, emission line spectrum, and absorption line spectrum, and how they linked to the stars. Okay, so a very quick reminder, what are photons? Well, photons are just simply packets of electromagnetic energy. How do we calculate the energy of a photon? We have seen that recently as well when we were looking at medical imaging. So the energy is equal to Planck's constant times the frequency of the electromagnetic wave. How is that linked to the wavelength? You know that the speed of any EM radiation is the frequency times the wavelength. So if we rearrange for frequency and substitute it in the equation, then we have energy is equal to Planck's constant times the speed of light divided by the wavelength of the wave. And as a quick reminder, 1 electron volt is a unit of energy. For when we measure small amounts of energy. Just to remind you, we saw electron volt for extremely small amount of energies. We also showed how to calculate that. Work done is equal to charge times potential difference. In this case, it has a very specific definition, and I hope you remember it. That is the amount of energy when an electron is accelerated by a potential difference of 1 volt. So I hope you remember that bit. Then we have the normal energy unit, joules, for quite normal size values, and then we have the kilowatt hour, which is power times time basically, but in terms of the power being in kilowatts and the time being in hours. And that's used for huge amounts of energy that are used at home. So this is what we will be focusing on this topic. So when it has to do with extremely small amount of energies, we look at electron volts. Now, electrons are all bound to an atom. However, there was something very weird about the way they behaved. They could only exist in discrete set of energies, which we call now energy levels. And what you see on the picture, you see what you will normally consider as an atom. So this is your atom. You have your nucleus in the center, and then you have the energy levels around it. Now, electrons can only occupy those energy levels. They can't exist between them. So that's what it means by they're bound to the atom. However, they can only exist in one of the discrete energy levels that exist around it. Now, if I were to redraw this diagram and just focus on one of its features, it would look like this. So this is where the nucleus will be. And I can represent the energy levels that way in the way they look. So the one closest to the nucleus, we call it n is equal to 1, then n is equal to 2, 3, 4, 5, and depending on what they have. There are some rules to know about this. So one of the rules is that the electrons cannot have energy between 2 energy levels. So I can't have 1 electron existing here at all. That does not work. It should be clearly on one of these energy levels. And it can move between those energy levels as well, depending on what is given to it. Now, an electron with zero energy is free from the atom. So at this level, whatever electron goes beyond that will escape from the atom. And the energy level with the most negative value is known as the ground state. So this is the ground state. Once again, is the one closest to the nucleus. And you can see the values are written in electron volts, and they're all negative. Now, the fact that they're negative shows that you need to provide the atom with external energy in order to remove the electron from the atom. So that's why they're all negative. So obviously, the further away from the nucleus, the less amount of energy will need to be provided for that specific electron to be fully released. Okay, so let's go to excitation and de-excitation. Now, what you see here are two diagrams, one that shows excitation and the other one that's showing de-excitation. We say an atom is excited if you provide external energy that causes the electron to move from a lower to a higher energy level. So from a lower to a higher energy level, we say that is excited. So let's say if this is n is equal to 1, this is n is equal to 2, and this is n is equal to 3. Now, if I want this electron here, that's sitting on this n is equal to 1, if I want it to move to a higher energy level, I need to provide it with the exact amount of energy. That's the difference between this energy level and this energy level. So if I want it to go from n is equal to 1 to n is equal to 2, then I need to provide it with with an external energy, which I can provide either by heating or by electromagnetic radiation, or by the electron absorbing a photon of a very specific amount of energy. So that energy needs to be exactly the difference between these two energy levels. Otherwise, the electron won't be able to. If it's just a bit less than the difference between those two energy levels, the electron will not go anywhere. If it's much more where it will lead it to here, it still will not be able to do that motion. It won't be able to go in between the energy levels. So for an electron to move to a higher energy level, it has to absorb, it has to be given energy or absorb a photon of the same amount of energy as the difference between the two energy levels. And when it absorbs it, it gets that energy, so it goes to a higher energy level. So it will go up to the second energy level, and you can see it here. Now, if I have an electron that's at a higher energy level, when there is space to go to a lower energy level, even though that's a bit more of a chemistry thing, we are interested only in the process and how it happens. So if I have an electron that is unstable and will go to a lower energy level, now you have it has extra energy. That energy will be released as a photon, and that photon will have exactly the same amount of energy as the difference between the two energy levels, which means that it will release a photon of a specific frequency or wavelength. We call this de-excitation. So if it goes from a higher to a lower energy level, it emits a photon. It doesn't absorb one. So in this case, it will absorb a photon. Here, it emits a photon of that specific amount of energy, and we need to consider the fact of conservation of energy. That's why you can create or destroy energy, which we call de-excitation when it goes from a higher to a lower energy level. So just to remind you, once again, these are considered the higher energy levels. These are considered the lower energy levels. Now, the most unique part of this is that each element has its own unique set of energy levels. So the energy levels of hydrogen are different from the energy levels of helium and lithium and so on. So no single element will have the same energy levels, which is quite unique because we can identify what elements each star have in their core, well, around their core at least, mostly, which we're going to see as well in a second. So it's like basically a fingerprint Each fingerprint is unique to the person, so you can identify what elements exist in a star based on analyzing the light coming from it, and we're going to see that. So how about doing calculations with this information? Well, if you're given a set of values for atomic energy levels of a particular element, it's very possible to calculate what wavelengths of radiation it can emit or absorb. And that will determine what type of element it is, since they already have studied all of them and they already know what energy levels they have. Now, if, for example, we're just going to do a very brief example here. Let's focus on this transition. So let's say I have an electron here and it de-excites and goes to a lower energy level. Now the energy here is 0.85, the energy there is 1.5. So I know that when this electron goes from the highest energy level to the third highest energy level, it will have a change of this much energy between the two values, so 1.5 minus 0.85. So I can see that the difference in the energy between those two energy levels is 0.65 electron volts. So I know the energy of the photon that will be emitted, since it's going from a high energy level to a lower energy level, it will emit a photon of that much energy. So this is the change in energy that we have calculated from one energy level to the other. And since I know that's a photon, and I know that I can calculate its frequency and its wavelength. So that will be, and by the way, I'm not asking the transition one, so just cross that out. So 0.65 times 1.6, sorry, for the electron volt. Remember to convert it to joules. 1.6 times 10 to the minus 19 is equal to the Planck's constant times the frequency. So that will be divided by the Planck's constant, divide both sides by Planck's constant. Okay, so your frequency will be 1.57 times 10 to the 14. And if you want to find the wavelength for that, you just simply divide it by the speed of light by the frequency. Just to cut it a bit short, that will be 1.91 times 10 to the minus 6 meters. So you can easily figure out what the frequency or wavelength of the photon will be based on the change in energy levels. The same thing can be done as well the other way around. So you can figure out how much energy was needed, for example, for an electron to go from a lower energy level to a higher energy level, just by if you're given the frequencies and wavelengths. So a quick check before we proceed. We have looked at the energy levels of electrons in isolated gas atoms, why they have negative values. We have also looked at the equations that could be used to calculate the frequency or energy depending on what you have. We also talked about how different atoms have different spectral lines. Well, not spectral lines, but different discrete energy levels, which we will combine in a second now with the emission and absorption line spectra. Okay, so here we're going to look at the last part of this lesson when it comes to analyzing light from stars. We call this spectroscopy, and it's basically used to identify elements within a star because it shows specific wavelengths of photons given off or absorbed by an element. So we will see this, it's actually absorbed mostly from the stars anyway, but we will see three different things that happen and how they are linked together. Now, the first thing that we could do is, let's say we had a light bulb of, any light bulb, any filament lamp, for example. Now, if I have the light, if I pass that light of a filament lamp through a diffraction grating, something that we have seen in a pack that we've done when we split the beam of laser in year 12. But don't worry, we will go again through it in the next lesson. So let's say I have a diffraction grating, so very small gaps that are used to split white light into its continuous spectrum. So I can do that to find out the continuous spectrum, and you can see that there are all the colors of the rainbow here, with no breaks between or anything. It's a continuous spectrum, so all the colors that exist, that's what we call it, a continuous spectrum. This comes from, like I said, any source of white light, like a filament lamp. Now, in terms of emission spectrum, it's very important to know the difference between emission and absorption spectrum. Obviously, you know that continuous spectrum should be all the colors of the rainbow just by passing white light through something. But when it comes to emission spectrum, what you have is a hot gas. So basically, you can put. We do have it in school. We have these tubes of glasses that have gases in them, and then we connect it to a device that we have in school, and it heats it up. And when it heats the gas up, and you place a diffraction grating in front of it, once again, you have to have a hot gas with diffraction grating in front of it. So you know that hot gas, heat in general, causes the electrons in an atom to go from a lower energy level to a higher energy level. Now, as they do that, they usually de-excite themselves, and through the excitation process, they emit light of a specific frequency, or they emit radiation, electromagnetic radiation of a specific frequency and hence wavelength. And this appears in a black backdrop as the bright lines that you see. And you see that this line will match this one here, so it will look exactly the same, but it will only have specific, obviously, frequencies. So in the emission spectrum, in reality, what we see is, so this is the energy levels in an atom. I forgot to mention before that also in an atom, when we show the energy levels, they are the distance is increasing, so the lower energy levels are closer together, and the higher you get, the further away they get from each other. What we see here is, for example, you have an electron there that's excited because it's the hot gas, so they already are excited, the electrons. This could drop from there to there, which will emit a photon of a specific wavelength, and that wavelength could be the wavelength of, for example, this line here that forms. So it will be, once it passes through diffraction grating, it will appear on a black backdrop as a colorful line. For example, this one could be the green line here, and this one could be the red line here. With the emission spectrum, is you already have something that's excited, an element, the gas of an element that's already excited, and as it de-excites, it drops to lower energy levels, which emit photons that we can see on the visible light spectrum of the electromagnetic spectrum. So what about absorption spectrum? Now, in an absorption spectrum, you have a source of light passing through cold gas. And as it passes through the cold, so basically what you have is the full spectrum of visible light. So you have the continuous spectrum, but as the continuous spectrum passes through a cold gas, instead of just passing through it, we know that gas could obviously have atoms in there. Now that those atoms, we know that any light anyway has a frequency of all the way, has the whole range of frequencies from red to violet. So as it passes from the light source to the cold gas, some of those wavelengths of the white light of the whole continuous spectrum will get absorbed by the atoms in the cold gas, and they will excite the atoms in there. So you'll have the energy levels going from a lower to a higher energy level, the electrons going from a lower to a higher energy level, because they will absorb a photon of that specific wavelength of frequency. So basically, if you pass that light through a diffraction grating, you will have the whole spectrum but you will have missing parts because those parts would have been absorbed by the atoms, by the electrons in the atoms of the cold gas. So another thing that you could notice here is how these lines, if it's the same element, only and only if it's the same element, these lines exactly match each other. So it's like a negative image of one another. And they exactly match together. And this is how we basically figure out what is going on in stars, like what elements they're made from. We usually do this in a lab. So we usually figure out the emission spectrum in a lab on Earth. And then we get the light coming from distant stars and we analyze it using the absorption spectra. And these two are mirror images of each other. But we'll see it a little bit in more depth now anyway. Remember that this will be a unique fingerprint, the emission spectrum or the absorption spectrum are unique to each different element that exists. This is a written of what's going on. So emission line spectrum. Remember, emission is when it emits photons in the black backdrop. So we see the colors of those photons emitted. So atoms in a hot gas are excited. The electrons from higher energy levels drop back down. That this means they emit photons with discrete frequency specific to the element. In the absorption line spectrum is a bit different. You have light from a source that produces a continuous spectrum. It passes through a cool gas, and as photons pass through the gas, some are absorbed by the gas atoms and excite them. And that's what appears as dark spots. So how is this used in stars? Well, if you consider that you have the core of a star, and then the extra gas around it, because we already have seen that in lesson 1 and 2. Well, lesson 1, actually. So let's say that's the core and that's the gas around it. Now, we assume that the core emits electromagnetic radiation of all the frequencies, well, especially for the visible light, since we know that it emits visible light. As that light passes through the gas, it gets absorbed by some of the, well, not all of it, obviously, because there's different elements. They're all are very specific to how much they will absorb of each one, since the energy levels have a specific energy requirement. So what you will see is the cooler outer layers of the of a star will absorb photons of specific wavelengths, which will appear as dark lines, and then we compare this to the known emission spectrum, to be more particular. Of elements to find out what elements a star is made from. Now, obviously, we said that if the electrons will go to a higher energy level, they obviously will go back to the lower energy level by re-emitting a photon. So in the case of the sun, for example, if I'm looking at the energy levels of, I don't know, let's say helium coming from the sun, then I will know that what will happen is that some of that electromagnetic radiation will be absorbed by an electron, which will cause it to go to a higher energy level. But usually electrons don't like staying at a higher energy level for too long, so they will drop back down, emitting the photon of the same wavelength. Now, why is it not seen on the spectra? Why don't we get to see it showing up in the spectra clearly if it's getting re-emitted? Well, they're actually scattered. When they get absorbed and then they get re-emitted, they usually are emitted in different directions, so they're scattered. So the intensity in the original direction is reduced, so you won't see that basically formed in the spectra, or missing from the spectra. So For a specific element, for example, the emission and absorption spectrum, like we said at the beginning, should look like a negative image of one another. However, emission line spectra tend to have more lines than the absorption spectra. Emission have more lines compared to their equivalent absorption spectra. Why is that? Okay, so I want us to imagine what happens in an absorption and an emission spectrum. Now, in absorption spectra, usually what you have are electrons always starting from the ground state and going higher up. However, with emission, they could start from anywhere and go to a lower energy level. So this is for the absorption spectra. What could happen in an absorption spectra in an atom, and this is for the emission. So here, photons of every frequency or wavelength that are involved in the spectra can be seen. Also, another one, the whole from the top to the bottom. However, in terms of absorption spectra, they usually start at the lowest energy level possible. So what you might be missing in an absorption spectra is this level, which is appearing here because it can drop from any single level, but it can't appear on this one. So this could be missing. Obviously, there's more lines as well. There's more energy levels in usually, more complex elements. But the idea is that that's missing, basically. That's why usually emission spectra have more lines compared to their equivalent absorption ones for the same element. So what scientists do is that they take the absorption line spectrum from a star, and they compare it to the emission line spectrum that they took in the lab. If we know the line spectrum for a particular element, then we can check whether that's present in the star, including for any star that's quite far, that we can still analyze its light. So if an element is present, then we will be able to match the characteristic pattern of the spectral lines to the dark lines in the characteristic pattern of the emission spectral lines to the dark lines in the absorption line spectrum of the star. Let's go back to the learning outcomes, and we are nearly done. So we looked at emission spectral lines coming from hot gases in terms of emission of photons between the discrete energy levels. Different atoms will have different spectral lines which can be used to identify elements within stars. And we talked about the continuous emission line and absorption line spectrum as well. So in the next lesson, we'll be looking at a few more things about analyzing the starlight and some new laws that have to do with the color and temperature of stars.